Welcome. On this video, we will introduce the idea of an inverse function. So let's get started. So we're going to start illustrating what an inverse function is by looking at some specific algorithm here. And this algorithm is going to help us understand what do we exactly mean by an inverse function. So an algorithm is just a series of steps. So let's follow these steps and let's take a look at some of the results. So we're going to start with a number. I don't know. Let's start with the value of 22. So we're going to start with the value and then we're going to add 5 to it. So that's going to give us 27. So we're done with the first step. And our second step, it's saying that whatever we got there, we need to divide it by 3. So 27 over 3, that's equivalent to 9. So that's our second step. Now the next step is saying take a look at your result and I'll take away 4, which is going to give us 5. And the last step is to just double the result, which in this case, if we multiply by 2, that's going to give us 10. So all we did here, we just did a series of steps. Now, under the first example, it says, well, now we know that the result of these steps right here was going to be 10, which is exactly what we got here. So now let's try to work it backwards. Now that we know the results, and let's try to see if we get the original number back. So what do we mean by working it backwards? Well, we're going to go, if by following these procedures, we follow this direction. So now we want to work backwards, we want to go on this direction. So if we want to go the opposite direction, so we know that we need to start with 10 because that was the result that we got here. So remember that in this procedure, we started with the value of 22 and then we end up with the value of 10. So we want to go backwards. We want to start with the value of 10 and we want to do this procedure swap backwards and let's see what we end up with. So we're going to start with 10 and then we're going on the opposite direction. We're going to do quite the opposite. So instead of doubling your result, I'm going to divide it by 2, which is going to be 5. And instead of subtracting 4, I'm going to do the opposite, which is going to be adding 4. And instead of dividing it by 3, I'm going to multiply by 3. And instead of adding 5, I want to subtract 5. So now notice that if we started with 10 and we did the procedures backwards, we end up with a value of 22. So this is a very good illustration of what an inverse function does. So what an inverse function does is does the opposite of what an originally function did. So what do we mean by that? Well, let's assume that this direction going backwards in black, it was a function. So in this function, we plug in 22 and we ended up with 10. Now, if we say that the red steps illustrates another function, this is saying that I plug in 10, I end up with 22, which is exactly the opposite here. So think about this as being the domain and being the range. So the domain of this function is 22 and the range of this function is 10. Then what an inverse function is, it gets the range of the original and it gives you the domain of the original. So it's just doing the opposite of what a function was originally doing. And to see an illustration of what I'm trying to say here is, well, we started with the function that started with 22 and it gives you 10. And let's call this function f of x. And what this f of s function did, it plugged in 22 and it gave you 10. So now this inverse function, what it did was quite the opposite. Let's call this function g of x. What this function did was quite the opposite. It plugged in 10 and it gives you 22 back. So notice that it kind of completes a full circle. You start by defining a function. The domain gives you a range. Well, the inverse, it gets the range and it gives you the original domain. That's what an inverse function exactly does. So now, since we already talked about f of x and g of x, let's try to define them using the steps that we did here. So is it possible for me to define those functions using the steps that we did here? Well, on f of x, let's define it. And again, f of x is going to be our function that we plug in a 22 and then we end up with a 10. what we did here, we started with a number. Let me just represent that with an x. And the first thing that I did, I added a 5 to it. Now on my next step, I got the result and I divided by 3. So I'm going to get my result and I'm going to divide it by 3. And then the result, we take away 4. So that's what I'm doing here. I'm just generalizing the algorithm. And then at the end, I got the overall result and I multiply it by 2. So notice that this function, it's essentially just doing what these steps were intended to do. And let's just try to simplify this. Let me just work with the inside. Let me make sure they have the same denominator. So now I can just rewrite this as x plus 5 over, this will be 12. 12 over 3. I'm just simplifying this. So now if we combine like terms, I'm going to end up with x minus 7 divided by 3, and I still have to multiply by 2. So if we do this correctly, we're going to get 2x minus 14 all over 3. So this function that we just created here is the function that it just did what this procedure in black was doing. And let's just call this f of x. Now, let's try to do quite the opposite. Now, let's try to come up with a function that does the opposite, which is g of x, which is going to illustrate what this red procedure was doing. So the first thing that I did, I got a value, and instead of doubling, I divided it by 2. So I'm going to get my value, and I'm going to divide it by 2. And then the next step, we added a 4 to it, and then we got the whole result, and we multiply it by 3. And then lastly, the whole result, we subtracted a 5 to it. So notice that this function that we are defining here is essentially defining the direction that we took in this blank, in this red ink here. So if we simplify this a little bit further, now notice that inside this big parenthesis here, that's going to give us x over 2 plus 8 over 2. Still going to multiply by 3. Still going to take away 5. Let me simplify this, and now it's going to give us inside of a big parenthesis, so we're going to get 8x over 2. I'm sorry, 8 plus x. Well, we get 8 plus x. And we're still going to multiply it 3. I'm just going to go a little bit fast here because this is just pure calculation. So now if we multiply by 3, this is going to give us 24 plus 3x all over 2. And again, this whole thing, we needed to subtract a 5. And if we do subtract 5, we're going to end up with 3x plus 14 over 2. So why are we defining these two functions? Well, we wanted to illustrate here that these two functions are what we call inverse function, because it is doing exactly the opposite procedures, but not everything is going to be, you're not going to be given the procedure. Sometimes you're going to be given an actual function and you're going to be asked to see, well, are those two functions inverse of each other? And right now we just show that they are inverse to each other because we literally took the steps of f of x and we just did the opposite to it. So that's what an inverse function should do. But now that we have these two functions defined, let's actually show algebraically some of those properties that actually inverse functions have with each other. So what are some properties that inverse functions have with each other? Well, let me just write down my functions one more time. So the first big relationship, or actually a property that we do have here, is that the domain of f of x is the range of g of x, and the opposite domain of g of x is actually the range of f of x. So what do we mean by this? Well, I mean, going back to our previous result, Notice that here we started with the value of 22 and then we end up with the value of 10. We said that f of x got the value of 22 and spit out the number 10, and g of x did the opposite. In other words, f of x had a domain of a value of 22 and then it gave you 10. Well, g of x was doing the opposite. To g of x, we plug in 10 and it gives me a value of 22 out. So this is the most important property when it comes to inverse functions. The domain and the range of inverse functions, they switch with each other. Now, what's the second property? Well, the second property is that the composition of inverse functions is always equal to the variable x. And this will always be true. So if we take out, let's do this example since we already know those functions. So if I take out the composition of f and g, which again, it is equivalent to just f parenthesis g. If I compose these two functions that I have already stated here, you will see that the result is always going to be x. So if two functions are defined to be inverse, if you compose them, they will always be equivalent to the variable x. So let's do that. Let's show that this is actually true. So we're going to go to our function f, which is right here, and then we're going to plug in the g on it. So let's see how this is going to look. I can already see that it's not going to look nice. So we got a 2, and then every time that we see an x on it, we're going to plug in the whole function. Oops, sorry. We're going to plug in this whole function. So here we go. So we're going to get 3x plus 14 over 2 minus 14. And now everything has to be divided by 3. So notice that all I did, I went to the function of f, and every time we saw an x, we plug in the whole function of g of x. So this is what we have now. And let's just try to simplify this, which I can already see that it's not going to look nice. So the first thing that you notice is that the 2's will cancel out, so that's good. So let's just continue our result here. So now we're going to get 3x plus 14 minus 14 all over 3. Oh, it's actually simple. So now notice that the 14's will cancel out. So now I get 3x over 3, which notice that the 3's will cancel out, and now x is remaining. And you will always going to have this result if two functions are defined to be inverse of each other. The composition will always be equivalent to x. And in this case, it doesn't really matter if we did f composed of g. We would have got the same result if we would have done g composed of f of x, which we're not going to do it. You can just verify it on your own, but you will see that this is just one of those specific scenarios where the order of the composition doesn't really matter. If you compose two inverse functions, regardless of the order, the result is always going to be equivalent to the variable x. And the last property that we're going to be discussing regarding inverse functions is that inverse functions are always reflected over the line y equals x. So what am I trying to say here? So if I get the function f of x and I reflect it, and if I reflect this function over the line y equals x, I am going to get the function g of x. And the other way around, if I get the function g of x and I reflect it over the line y equals x, I am going to get the function f of x. So let's show this. Now let's go to here to our small activity here. So notice I already took the liberty of just writing down the function. Here we have the f of x that we started our discussion with. Here we have g of x that we started our discussion with. Without the line, notice that this is f of x. I'm sorry, the red is f of x, and the blue is g of x. And now notice that if I draw the line y equals x, any point in f of x, and if I reflect over the line y equals x, I am going to get the red function. So get this section, get this blue section, and if I reflect it over the line y equals x, notice that I'm going to be landing on the right line. And the other way around, if I get the red line, and if I reflect it over the line y equals x, I am going to get the blue line. And it's also the same right here on the bottom. If I get the blue line, which it is a reflection of g of x, and if I reflect it over the line y equals x, I am going to get the red line, which is f of x. And the other way around, if I get f of x, and if I reflect it over the line y equals x, I am going to get the blue line, which is g of x. So these are the three big properties that inverse functions have. The first one being the domain and the range, they switch with each other. The second one being the composition of inverse functions are always equivalent to just the variable x. And the last being that if I get one function and if I reflect it over the line y equals x, I'm always going to get the inverse function. And again, the big idea of an inverse function, it was illustrated right here with our algorithm that we started a conversation with. Pretty much an inverse function, it just undoes what the original function was doing. So here we got a 22, we did a bunch of procedures and ended up with 10. Well, the inverse function is going to get the result. It's going to do the procedures in an opposite manner and it's going to give you the original value back. So hopefully this was helpful. And with this, it concludes our lesson with inverse functions as an introduction.